In the morning, you put on socks first, then shoes. At night, you take off shoes first, then socks. To undo a sequence, you reverse the order. Matrix inverses follow exactly the same logic. If you multiply A times B, the inverse is not A inverse times B inverse. That keeps the original order and it's wrong. The correct inverse of AB is B inverse times A inverse. The order flips. Just like the socks and shoes analogy, the last thing you put on is the first thing you take off. Here's the formal rule. If A and B are both invertible n by n matrices, then their product A times B is also invertible, and its inverse equals B inverse times A inverse. Notice the key detail. The order reverses. It's B inverse times A inverse, not A inverse times B inverse. Now, what does it mean for a matrix to be invertible? An invertible matrix is one that has an inverse. A matrix A inverse satisfying two conditions. A times A inverse equals the identity matrix, and A inverse times A equals the identity matrix. The identity matrix acts like the number 1 in regular multiplication. Multiplying any matrix by it changes nothing. Let's verify that this formula actually works. We need to show that AB multiplied by B inverse A inverse equals the identity matrix. Start by writing out the full product. ABB inverse A inverse. Now matrix multiplication is associative, so we can group any adjacent pair together. Look at the center of this expression. B sits right next to B inverse. B times B inverse equals the identity matrix, so we replace that pair with I. Now we have A times I times A inverse. Multiplying any matrix by the identity changes nothing, so this simplifies to just A times A inverse, and A times A inverse equals the identity. The entire product collapses down to I. Notice how the cancellation works from the inside out. B and B inverse are the inner pair. They meet and cancel first. Then A and A inverse become adjacent and cancel second. This inside-out collapse is exactly why the order in the inverse must reverse. The definition of an inverse requires checking both sides. So let's confirm the other direction. B inverse, A inverse times AB also equals the identity. This time, A inverse and A are the inner pair. A inverse times A equals I. That leaves B inverse times I times B, which simplifies to B inverse times B, which equals I. Both checks now pass, confirming that B inverse A inverse is indeed the inverse of AB. Inverses reverse the order of a product. It turns out transposes do the exact same thing. The transpose of A times B equals B transpose times A transpose. The order flips here too. Reversal is the recurring theme in linear algebra, and this makes sense. Matrix multiplication is not commutative, so pushing an operation through a product forces the factor order to reverse. Notice the same structural pattern. In both cases, the order reverses. Right? Keep this transpose rule in mind. We need it right now. Here's an elegant result. The inverse of A transpose equals the transpose of A inverse. These two operations, taking the inverse and taking the transpose, commute with each other. Let's prove it. Start from a known fact. A times A inverse equals the identity. Now transpose both sides of this equation. On the left side, we get the transpose of the product A times A inverse. Apply the product transpose rule from earlier. Remember, the order reverses, so this becomes A inverse transpose times A transpose. On the right side, the transpose of the identity is just the identity itself, since the identity matrix is symmetric. Now read the resulting equation. Inverse transpose times A transpose equals the identity. By definition, this means that A inverse transpose is the inverse of A transpose, and we are done. The inverse of A transpose equals the transpose of A inverse. They are two names for the same matrix. 2 points of common confusion. First, this pattern extends beyond two matrices. The inverse of ABC equals C inverse B inverse A inverse. Every factor inverts and the entire sequence reverses. Second, keeping the original order fails. Watch what happens when you multiply AB by A inverse B inverse using the original order instead of the reversed order. You get A times BA inverse times B inverse. But the middle term, BA inverse, does not simplify to the identity because matrix multiplication is not commutative. So the product is stuck and does not equal I. Now compare with the correct order, multiply AB by B inverse A inverse, you get A times BB inverse times A inverse. The middle term BB inverse equals I. So this simplifies to A times I times A inverse, which equals AA inverse, which equals I. The reversal is essential, not optional. Let's pull everything together into a clean summary. Here are 3 rules to carry with you. Rule 1, the inverse of a product reverses the order. The inverse of AB equals B inverse times A inverse. The order reverses. Rule 2, the transpose of a product also reverses the order. The transpose of AB equals B transpose times A transpose. Again, the order reverses. Rule 3, for a single matrix, transpose and inverse commute. The inverse of A transpose equals the transpose of A inverse. These 2 operations can be done in either order. The unifying principle behind all of this, pushing an operation like inverse or transpose through a product reverses the factor order. You will use these rules constantly when solving matrix equations in least squares problems where the expression A transpose A inverse times A transpose appears and improves throughout linear algebra. Master the reversal instinct and these manipulations will become second nature.